There are two types of regions that we're going to learn how to integrate over that are not going to be rectangles. So I've drawn a rectangle here. That's the region that we know how to integrate over. And then I've drawn an example of a type 1 and a type 2 region. And here's the basic idea. With a rectangle, it has 4 boundaries. We have a left side and a right side and a top and a bottom. Okay, and all of those are given by constants. So the left and the right side are given by x being constant. That gives me vertical lines in the xy plane. The top and the bottom boundaries are y being constant. That gives me 2 horizontal lines. Now with type 1 and type 2 regions, we're going to keep 2 of the boundaries as constant, either the left and the right or the top and the bottom. But we're going to replace the other 2 with continuous functions. So a type 1 region would be something where I've got constant boundaries on the left and the right side. So x is varying from a fixed number a to a fixed number b, but the bottom and the top boundaries I'm going to replace with y equals g1 of x and y equals g2 of x, where those are going to be continuous functions. So the top and the bottom are allowed to curve. Okay. Now, as I've drawn this particular example here, I've got 2 walls and a floor and a ceiling still. It's just that the floor and the ceiling curve. It would be entirely possible for me to have something like so, and I could still define that as a type 1 region. What's happening here is that at this point right here, that's where the floor and the ceiling meet. Now here, the floor and the ceiling didn't meet, so I had to have this stretch of wall to connect the floor and the ceiling. Here they meet, so there's only one point. But that line, x equals a, would still be my left boundary. We just don't have a very high wall. We have an infinitesimally high wall because it just consists of a single point. So there will be plenty of times where we see things like this, where the floor and the ceiling meet, and so my left boundary or my right boundary is really just a single point. Okay. A type 2 region, same basic idea, but here we keep the top and the bottom boundaries as constant, and we let the 2 walls be continuous functions. So the left side would be x is h1 of y, a continuous function of y, and the right boundary is x is another continuous function of y. All right. Now, when we're working with a rectangle, we know we always want to do things as an iterated integral, okay? And so we're essentially doing volumes by slicing. We're doing signed volumes by slicing. And with a rectangle, I can slice it either way. I can slice it vertically, I can slice it horizontally, and unless the integrand makes one of those options better than the other, it really doesn't make much difference. With type 1 and type 2 regions, it absolutely matters. I should mention, by the way, I don't care if you know that this one is type 1 and that one is type 2. I care that you can use type 1 and type 2 regions. So knowing that either the left and the right or the top and the bottom are constants and the other 2 are allowed to be functions. They could still be constant, but they don't have to be. Okay. So a rectangle is actually an example of a region that's both type 1 and type 2. It's just that the continuous functions that we have happen to be constant functions. Okay, now if I'm working with something like this, okay, it's always going to be that I'm going to slice things parallel to the sides that were constant. So I would have to draw my slices this way. Okay. So I can imagine that if I'm integrating over some region, we'll call this region R, f of xy dA, okay, so the function is giving me z values, which as I've drawn this would be sticking out from the board or sticking back behind the board. Okay. Along each one of these slices, I've basically got some stuff sticking out from the board. I'm going to calculate that cross-sectional area first. So that means I'm going to be integrating first from the bottom to the top. but that means I'm integrating from g1 of x to g2 of x, f of xy dy. That gives me my cross-sectional area. Then I multiply that by the thickness of the slice and add up all of the slices. That's integrating from a to b dx. Okay. So the rule is I'm now allowed to have functions as my limits of integration, but it's always functions inside, numbers outside. Because what's going to happen is I start here with something that has both x's and y's in it. Okay? Then I find an antiderivative in terms of y. Oops, that's g2 of x. Okay. And I'm going to replace y with this function of x. Once I've done that inside integral, there are no more y's in there. All the y's got replaced with some x's. Then I integrate that, and I replace the x's with a's and b's. I end up with a number. There are no variables in my final answer. And for a definite integral, I'm supposed to end up with a number. If I had these switched so that I had functions on the outside, the very last thing I'd be doing would be plugging in a variable. I wouldn't be getting a number. Okay. So the order absolutely matters. And you'll find I think it's really helpful to draw in the slicing, so I always do. Okay. So here, if it's a type 2 region, and again, I don't care if you know the name, I care that you know, hey, the top and bottom are constant, the left and right can wiggle. Okay? So I'm going to slice parallel to those constant boundaries here. Okay? And so then I'm always integrating along the slice, so from left to right. So I would go from h1 of y to h2 of y. And do remember, we always go bottom to top or left to right, because we're always setting it up so that our dA, the area of the base, counts as positive. The only thing that contributes to negative volume would be a negative height. Okay, so we would have f of xy. This is dx. And then the thickness of this slice is a small change in y. That's like a dy. So we multiply by the thickness of the slice, and we add them all up and take the limit, and that, of course, is my integration with respect to y. Okay, excellent. So that is type 1 and type 2 regions. I'd like to just do an example so that we can see how each time we integrate, we go down one in the number of variables that we have. And then often the toughest things when we're doing integrals of functions of more than one variable is not so much the integration, but setting up the limits of integration. So I want to also just practice some of that. Okay, so let's suppose that my region R is this triangular region here. And again, I can call it R. R did not stand for rectangle. R stood for region. I could also call it D if I wanted to. My choice what I want to name it. Okay, and I would like to find the double integral over R. Well, let's just do x plus y dA. Notice, as long as I'm writing just one symbol here to describe the region, I'm not putting a dx and a dy. I don't do that until I have individual limits of integration, and then the order in which I put them tells me the order in which I'm integrating. Okay, now this triangular region is actually both type 1 and type 2. I can sort of see, if I wanted to make the left and the right sides constant, well, my left side is x equals 0. My right side, well, the floor and the ceiling are sort of meeting right here, but my right side is just that line x equals 1 right there. Now the bottom boundary happens to also be constant, because that would be y equals 0, but the top boundary isn't. I can see this top boundary is this linear function. So let's see, the slope is -2, and the y-intercept is 2. So it's -2x plus 2. So if I were describing it as a type 1 region, I would choose to have my x values constants and my y's as a function of x. If I preferred, I could describe it as a type 2 region, because we said the bottom was constant, that was y equals 0. If I want to view this as the left wall and the right wall meet, they meet up here at a height of y equals 2. This would be x equals 0 is the left side. And then here, I would just need to solve for x as a function of y. Okay. Because if I'm describing what happens as this is the right side, a y value isn't a boundary for the right side. It's x values that measure how far left and right I am. So I'd take this equation, but I'd have to solve it for x. So I'd get, let's see, y minus 2 divided by negative 2 is equal to x, and I'd probably change that to 2 minus y over 2. Okay, now I can do either one. I usually prefer this. I'm more used to having y as a function of x than x as a function of y. So if I have a choice, I almost always go with this, which happens to be the one that's type 1. So I can remember which one is type 1 versus type 2. I just don't consider it important enough to really devote any brain cells to. I want to know how to do this. Okay, so working with it this way, I would say, okay, that means slice things this way. I find it really helpful, as I mentioned, to draw in those slices, because when I'm calculating my cross-sectional areas, I'm going to be integrating along this slice. Again, I can imagine that my function is spitting out some z values, so I'm getting this cross-sectional area that's sticking out from the board, but I'm getting that by integrating from bottom to top. And I can see that the top of my slices is not just 2. The top of my slice varies. The very top of that slice is 2. That's the only slice that goes that high. So we're going to be going from 0 to negative 2x plus 2, and we're integrating x plus y. That's my dy. And then we've got to add up the slices and multiply by the thickness of the slice. The slices start at an x value of 0 and end at an x value of 1. Okay. If you set up an integral in rectangular coordinates and all your limits of integration are constant, you are integrating over a rectangle. If you're not integrating over a rectangle and you're in rectangular coordinates with constant limits, you've set it up wrong. Okay. So that's why I like to draw in the slices, because when you're thinking top, your eyes might tend to go to the top of the shape. But if I'm thinking top of the slice, I see that that depends on which slice I'm in, so that I should be getting a function. All right, so let's go ahead and integrate. So this is going to be the integral from 0 to 1. We're integrating with respect to y. So I'm going to get xy plus y squared over 2. And that's evaluated between negative 2x plus 2 and 0. And then we'll still have to integrate that with respect to x. So that's the integral from 0 to 1 of x times negative 2x plus 2 plus y squared is going to be negative 2x plus 2 quantity squared over 2. And we've got to integrate that with respect to x. Now, I'm going to need to do a little bit of algebra before I integrate. But let me just point out, we've done the first integral. Before we did that, we had two variables in here. We had x's and y's. Now that we've done that first integral, we replaced those y's with this function of x and 0. We've only got x's. So each time we integrate, we're going to lose a variable. All right, so this is the integral from 0 to 1 of negative 2x squared plus 2x plus, I'm going to just square this. So that's going to be 4x squared minus 8x plus 4 all over 2. And we've still got to integrate that dx. So let's see. 4x squared over 2 is going to be 2x squared, and that'll cancel with this piece. Here I've got 2x. This is going to be negative 8x over 2. That's going to be negative 4x. 2x minus 4x is negative 2x. And then 4 over 2 will give me a plus 2. That's not so bad. Okay, so that's going to be negative x squared plus 2x evaluated between 1 and 0. And so that's going to be negative 1 plus 2. And when I plug in 0, I do in fact just get 0. And so we get 1. Excellent.